So based on what they found with the 10 cases, they went back and looked at 361 cases of heart transplant cases dating back to 1986. 71 of these resulted in death. So once again, here's some printout from the one proportion applet to generate the null distribution of number of deaths. So here's the number. And once again, success feels unnatural because it's deaths, but remember, it's how we set up our hypothesis, or the null distribution of proportion of deaths, and here's the proportions. And this is out of the 361 cases, assuming the mortality rate for heart transplants at St. George's was 15%. So that benchmark. So we're assuming when we set this up that, so I filled this in being 15%. The sample size is 361. Now I'm going to take 1,000 samples. So I run this, there's 1,000 dots in each of these plots. And I'm interested in as extreme or more extreme than 71 because that's the number of deaths that we had. So set up the calculation for the exact binomial, and we're going to keep this really simple. We're just going to say we're interested in how many times or what the probability is for at least 71 or more. So here we can see 71 and then as extreme or more extreme. So any of the cases out here are what we're going to be counting. And so looking at that, when I did this, it actually told me that there were 10 out of the 1,000 cases. So I end up with 0.010. Now that is based on the simulation. If I click the exact binomial, it does this calculation for me and ends up being 0.0097. And that is right from the applet. Does this provide strong evidence that the mortality rate at St. George's is higher than 15%? How are you deciding? Well, looking at our new p-hat, it is now the 71 out of 361, which gives me 0.197. I say, given the very small p-value, St. George's does have a higher mortality rate. We have strong evidence here, very strong evidence that their rate is higher than the 15%. Now, before we move on to looking at the normal approximation base, so here we've done it by simulation. Here we did the count, and that's the actual count of the numbers here. We also had the computer actually do it by calculating the exact binomial for us. I want to go through the applet one time just to make sure everyone sees it and sees how to put the information into the applet. Remember, this one would be too difficult to do by hand. So I'm going to pause for a moment, go over to the applet, and I'll be right back. So here we are. Yours is going to look a little bit different because this is in my view of Canvas. But if I click on Web Applets, I'm going to go down. We're looking at statistical inference. That's what we're working on now. One proportion, because we're looking at just one proportion. Now here, probability of heads. This is strictly if you're doing, a coin toss. But here, we're looking at the 15%. And that changes it to pi, which is also the same thing as p that we use. And that's the notation our textbook uses, a p instead of pi. The sample size is going to be 361. Now, we don't want to just do this once. We could just draw one sample, and we have 313 failures and 48 successes. Okay. We want to do it lots and lots of times, though. So I'm going to do 999 more times to get us to 1,000. There we go. If I count the number of successes as extreme or more extreme than 71, I end up with 7. Now, it's not exactly what we got, what's in your handout, because obviously samples vary. Remember, as we take a sample, there's going to vary. Like when we flipped the coins, everyone spent time flipping the coin. If you did it at home, we do it in class, and some people will get 3 heads out of 10, some people will get 7 heads out of 10, but samples vary. I also can click the exact binomial, and there it is. It gives me that. I can show my summary statistics. So there's my mean and my standard deviation. If I want to change it to proportions, There we go. My mean for these remember are all p hats in here. The mean is 0.149, which is very close to the 0.15. And there's my standard deviation. So now we've calculated the p-value using a simulation, which we did here, using the p-value, using the binomial, which we did here. Hopefully, though, we can use that power of that normal curve, that bell curve, to hopefully help us have another method of calculating p-values. So another way to compute an approximate p-value, which works well, but only when sample size is reasonably large. So in which case do you think the null distribution would have more of a bell-shaped distribution? When n is 10 and p equals 0.5, or when n is 361 and p equals 0.15, and explain. Let's start with the case of n equals 10 and see what happens. So I'm going to look at n times p, and that's going to be 10 times 0.15, which gives me 1.5. Remember, we already said that it has to be, with that central limit theorem, it has to be at least 10. This is less than 10. So can I use, according to that central limit theorem, going back a ways here, remember, we need at least 10 successes and 10 failures. We don't have that. So we can't use this power of the central limit theorem, which allows us to use that normal approximation for the p-value. So the normal approximation does not apply. And that's per that central limit theorem. Now let's try n times p in the n equals 361 case. So we get 361 times 0.15, and we get 54.15. Well, that's definitely greater than or equal to 10. If I tried n times 1 minus p, you're like, well, I'm going to be multiplying it by a bigger number, because 1 minus 1.1, 1 minus 0.15 gives me 0.85. True, but you still want to do the calculation. That's at least 10. Based on that central limit theorem, the normal approximation does apply. Alrighty, so can we use the power of that? Definitely. On the null distribution of p hat, as given below, indicate where the observed value of the statistic is. Well, we figured out that p hat, in this case, was the 71 divided by the 361, which gives me 0.197. And that's right about here, I'm going to say. There's where my p hat would be from the study. Okay. First, verify the mean and standard deviation of the null distribution, and then calculate how many standard deviations from the mean of the null distribution the observed statistic is. What we're getting back to is that z-test again. So what I'm going to do here, this is based on remember, this is just based on what the applet gave us. So this is simulation. But let's see if the simulation value is close to what we get using that central limit theorem. So I'm going to pause. What I suggest doing first is writing down the null and alternate hypothesis. So there's the null. Can you write the alternate? Please pause. Also write down what the mean is and figure out the standard deviation using that central limit theorem. And come back and check your answer. So before we move on and before you check your work, I'm going to label these, indicate where the observed statistic is, and this is where it is, 0.197, and that's rough, as long as we're close to the general area of where it would be. And then it says verify the mean and standard deviation of the null distribution. So I wrote out the null and alternate hypotheses, and then I said, okay, well, the mean is, we're told is 0.15 because that's the benchmark we're using. The standard deviation, according to the central limit theorem, is the p times 1 minus p over n, and take the square root of that value. And I end up with 0.0187, which is really close to what I got here of 0.019 using simulation. So it's all looking good. And that's, I'm going to call that step 2. And then finally, it says, then calculate how many standard deviations from the mean of the null distribution this observed statistic is. Now remember, that's going to be that z-score. We're going to take whatever the p hat is, our observation, what we observed, minus whatever the value we're comparing it to is, the center, and the center in this case is 0.15 over that standard deviation of this curve in particular. So z in this case would be, we got 0.187. Oops, excuse me, no, we don't. We have 0.197, that's the p hat, minus 0.15, that's where we, assuming that's what we centered it on, divided by 0. And I'm going to round this up to 0.019 to make the calculation a little bit easier. And I end up with 2.47. So St. George's mortality rate is 2.47 standard deviations above the hypothesized value. So that's what we're looking at. So recall that the z-score is a standardized measure of how many standard deviations an observation is from the mean. A test statistic is the formal term for a standardized statistic that measures how far the observed statistic is from the value of the parameter hypothesized by the null hypothesis. When we're dealing with categorical variables, we're going to say null is p equals p sub 0. That's p naught. P naught, not p sub 0 is better terminology. The test statistic is now z equals, so it's z like we did before, the observed value, our p hat, minus our hypothesized value over that standard deviation that I calculated personally separately. I think it's a little bit easier to deal with. Using the empirical rule, going back in time, does the observed statistic from the study appear to be unusually far away from the hypothesized value? How are you deciding? And I'm going to say, well, do we think it's kind of far out? Remember, think back to the empirical rule. Plus or minus 2 standard deviations away, what percentage of the curve is under the curve is within 2 standard deviations? And hopefully you remember, oh, right. If I think about here, the normal curve, and I do plus or minus 2 standard deviations, that's plus 2 standard deviations, 95% fall in here. We ended up at 2.47. So are we pretty far on the tail? Yes. So we can, how am I deciding? It's beyond 2 standard deviations above the hypothesized value. Part O, sketch the null distribution and shade the region of the null distribution that represents the p-value. Then use the test statistic z and the standard normal table to determine the p-value. And this is also the method of finding the p-value using the z-score corresponding to the p-hat in standard normal table is called the one proportion z-test. So what we're doing is carrying out a one proportion z-test. So if I did a quick sketch, doesn't have to be perfect. So the null is assuming 0.15 is what as our hypothesized value. We're interested in the p-hat as extreme or more extreme. So that's what we want. We already know the z-score is 2.47. We found that. Now, if we look for the area under the curve, remember it's always going to be on this side. And if you look in the table, you're going to see that that's 0.9932. So our p-value, remember we want this side, is going to be 1 minus 0.9932, which gives us 0.0068. That's a really small p-value. So how well do the simulation-based and the exact binomial p-values match? Well, they're close. Okay, so if you look at the different p-values, we find that we're ending up, there's that normal approximation-based p-value, and then we have earlier, Keep going up. We have the exact binomial. It's very small and it's close. And then we have it with simulation. All these numbers are very close to each other. Close. Now, state a conclusion about the study based on the normal approximation-based p-value. Be sure to provide justification. One caution I want to give is remember, we can never find evidence for the null. We can never find evidence that it is 15% in this case. Okay. We can find evidence against the null. We can find evidence to support the alternate hypothesis, but not evidence for the null. Because remember, the null is we can't find evidence that it's just randomly happening. Okay. So take a moment, pause the video, and see and come up with a conclusion here. So what I wrote up is based on a very small p-value, and I give you the value from that normal approximation. We have very strong evidence that the mortality rate for all such heart transplant cases as St. George's, this should have been an S, sorry about that. Whoops. George's Hospital is higher than the 15%. And of course, your wording may be slightly different, that's fine, but you want to get that idea, you want to show the support that you have and what conclusion you're drawing in terms of what you found in the context of the research question we had.